Okay, the recording is going to start. I think we can begin. Okay, the lesson of today will be focused on an important problem in electrodynamics, which is commonly known as the Sommerfeld half-space problem. With this week, we start applying the theory developed so far to practical configurations, and this week we will address problems in the time harmonic regime, whereas in the next week we will see something about transient electromagnetics. What is the Sommerfeld half-space problem? Well, perhaps this is the simplest planar multi-layer configuration, besides, of course, free space. In Sommerfeld problem, we need to find the potential produced by a vertical electric dipole, VED, which, as you can see in this slide, is placed in a vacuum in the presence of a generally lossy dielectric half space. So you see here the vertical electric dipole is placed at the abscissa Z prime along the vertical Z direction. The origin of the reference system is at the interface between the lower half space, filled with a vacuum, and the upper half space, which is filled with a dielectric, which we will assume for simplicity to be non-magnetic, and so characterized by a generally complex relative permittivity epsilon r. As I said, we are in a time harmonic regime, and the time dependence that we will assume is of this kind, the exponential e to j omega t, where omega is, of course, the radiant frequency. And our bed is mathematically represented by a point source. There is a source located at a single point in space, so the dependence on the spatial coordinates of the source is given by these delta functions, P0 being a complex amplitude, which is expressed in an ampere times meter. Okay, let us see how to solve this problem. First of all, let us consider what we call the incident field. That is the field that will be present in the absence of the upper dielectric half space. So we are now in a free space entirely filled with vacuum, and we define the radial distance from dipole with this letter, capital R, which is, of course, the square root of rho squared plus z minus z prime squared. Okay, and the incident potential is very well known. It admits a closed form, which is nothing but the free space Green's function for the scalar Helmholtz equation. So we have basically a spherical wave, the exponential e2 minus j k1 r over 4 pi r times the amplitude of the source, p0. Okay. However, this is a spherical wave, and we need to calculate its interaction with a planar interface, something which cannot be done in a closed form. So it is convenient to express the spherical wave in terms of plane waves. That is because we are able to describe in simple terms the interaction of a plane wave with a planar interface. So what we need is to find the plane wave spectrum of our spherical wave. And to this aim, we can use the so-called Weil identity, which gives us exactly what we need. As you can see at the left-hand side, we have the spherical wave, the free space Green's function, and at the right-hand side, we have a double Fourier integral, so an integral made with respect to the spectral variables kx and ky, which are the components of the vector kt, where t stands for transverse. Inside the integral, we have the Fourier exponential, e2 minus j, the dot product of the vector kt and the transverse position vector rho. And what remains is this ratio, this fraction here, which is nothing but the one-dimensional Green's function for the one-dimensional Helmholtz equation, which is another exponential, e2 minus j kz1 times the absolute value of z minus z prime divided by 2j kz1, where this kz1 is a vertical wave number defined inside the medium 1, so this is the reason of the subscript, And the separation condition tells us that this wave number is equal to the square root of k1 squared, that is the square of the wave number in the medium 1, minus kt dot kt. Of course, as always, the square root is not uniquely defined, so we need to choose one of the two determinations of the square root, and we will choose the one whose imaginary part is negative. That is because in this way, the exponential that is inside this 1D Green's function is a vanishing function at infinity, and so the evanescent waves in the spectrum decay exponentially at infinity, whereas with the opposite determination, the one with imaginary part larger than 0, this exponential for the evanescent part of the spectrum would grow exponentially at infinity, which is, of course, something non-physical for the considered problem. Okay, so basically our valid identity expresses the spherical function on the left-hand side as an integral superposition of plane waves, because inside the integral we only have exponentials and thus plane waves. Okay, for each of those plane waves we are able to describe the interaction with the planar interface, because that's the elementary problem of plane wave incidence, and so reflection and refraction upon a planar interface. In particular, since the field is purely TM, our plane wave will be vertically polarized, and so its reflection, the relevant reflection coefficient is the one given here, where we need to employ the characteristic impedances of the transmission lines for TM waves. And so the reflection coefficient gamma with the superscript Tm is equal to the ratio between kz2 minus epsilon r kz1 and kz2 plus epsilon r kz1, where, of course, kz2 is the vertical wave number inside the dielectric. Okay. Note that the reflected plane wave, as well as the transmitted plane wave, everything here is transverse magnetic, so Tm. That is because, as we know by elementary electromagnetics, incidence upon a planar interface with isotropic media does not introduce cross-polarization. So if we have an incident TM plane wave, we have a scattered, that is reflected and refracted TM plane waves. But there is even more. In general, the reflection coefficient depends on the incident angle. However, it depends only on the angle between the direction of incidence and the normal to the interface, the angle that here is called with capital theta, and it is instead independent of the azimuthal angle, capital phi. That is, in other words, the reflection coefficient, as you can see here, depends only on k rho, which is the amplitude of the transverse wave vector kt, where this transverse wave vector explicitly has Cartesian components represented here in terms of the angles capital theta and capital phi. In particular, we can write the vertical wave number inside the vacuum in terms of those angles as k1 times cosine theta, as you can see with simple geometrical considerations. Okay, so we can now write the reflected potential by simply inserting this coefficient minus gamma Tm inside the Weil representation for the incident wave. Okay, where, note, we have here changed the sign in the exponential in order to have a wave that propagates in the negative z direction. Okay. Note also that there is a minus sign in front of the reflection coefficient, and the reason is that we are considering the z component of the vector magnetic potential A. And as you may recall from basic electromagnetic courses, this component is associated to a current rather than to a voltage in an equivalent transmission line model. In fact, for each plane wave, we can represent the z component of the magnetic potential AZ in a factorized form, that is a longitudinal function L of z times a transverse function t, which depends on the transverse position vector rho. And the latter in particular is simply the transverse exponential of any plane wave. Well, it is possible to represent the transverse fields ht and et in terms of the potential, as you can see here. And also the fields will have a factorized form in which you can see the z dependence is given by minus L for the magnetic field, and by this blue term, 1 over j omega epsilon times the derivative of L with respect to z for the transverse electric field. The latter is the equivalent voltage, whereas minus L is the equivalent current. And as you can see, L is what occurs inside AZ. So AZ is proportional to the current. And for this reason, we need to employ a current reflection coefficient instead of a voltage reflection coefficient. Since gamma is by itself a voltage reflection coefficient, we need to insert a minus sign in order to get the current reflection coefficient, okay? Once we have this expression, we are now in a position of calculating also the transmitted potential. And we do that by matching the fields at the interface, because at the lower vacuum dielectric interface, z equal 0 minus, the total potential is just the sum of the incident and reflected waves. So you can see here inside the integral 1 minus gamma Tm. 1 comes from the incident wave and gamma Tm comes from the reflected wave. Now, the continuity of the equivalent current across the interface, which derives from the continuity of the tangential component of the magnetic field, implies the continuity of AZ across the interface. So we may enforce that AZ at 0 minus is equal to AZ at 0 plus. And we can simply call this AZ without at z equals 0 without specifying plus or minus. So if we know the potential at the interface, we can simply write the transmitted potential by letting each plane wave propagate according to the correct exponential, which is e2 minus j kz2z, because now we are inside medium 2, okay? So you can see the wave number kz2. Okay, which is, of course, again given by the square root of k2 squared minus kt dot kt. So, to summarize, here is the expression of our potential. This is the potential everywhere. In the lower half space as the sum of the incident potential, which is known in a closed form, and the reflected potential, which is given by a Fourier integral, and in the upper half space, where it is given by another Fourier integral. Okay. It is possible, however, to modify this expression, which is an expression in terms of double Fourier integrals of this kind, by noting that the integrand depends only on k rho. This is because of the rotational symmetry of the problem. And in fact, if we now introduce polar variables, so k rho and capital phi in the spectral plane kx, ky, and we also introduce polar variables in the transverse spatial plane, so rho and small phi. If we now change variables inside our double Fourier integrals, what we get is a double integral with respect to k rho, with integration limits from 0 to infinity, and with respect to capital phi, with integration limits from 0 to double pi. We exchange those two integrations, and we note that the inner integral, the azimuthal integral, can be closed analytically because it is equal up to the constant 2 pi to the Bessel function j of 0 order and argument k rho rho. So we are able to perform analytically this integration, and we discover that the result is independent of the azimuthal spectral angle capital phi. So in the end, what we get is a representation of the potential in terms of a single spectral integral instead of a double spectral integral, which is an advantage. And this integral has the canonical form of an inverse Hankel transform of order 0, because we have a function f tilde of k rho multiplied by a Bessel function of order 0 times the wave number k rho, and this is integrated with respect to k rho. Technically, this is known as a Sommerfeld integral of order 0, and we may note it as S0 of f tilde. Okay. As a consequence of this representation, we also have that the potential only depends on rho, as we would expect, since the configuration is omnidirectional, that is, has rotational symmetry around the z-axis. So everything should be independent of the azimuthal spatial coordinate small phi. Okay, so having noted this, we can rewrite our solution to the Sommerfeld problem in terms of single spectral integrals that are Sommerfeld integrals. Okay, the one for the reflected wave here in the lower half space, and the one for the transmitted wave in the upper half space. Note that in this representation, we have that the integrand of those integrals contains a Bessel function along the radial coordinate rho, and the Bessel function has the character of a standing wave. As you may remind, Bessel functions asymptotically behave like trigonometric functions, cosines and sines. Whereas with respect to the vertical direction, we have complex exponentials, which are typically used to represent propagating waves. So for this reason, this kind of representation is also termed an axial transmission representation. So the elementary waves involved as integrands in this representation are waves that propagate in the axial direction, that is the direction of the vertical axis z. Okay. Now, of course, in general, we are not able to close analytically those integrals, which must be evaluated numerically. But what's interesting now is to explore the integrand of those integrals. And to this aim, let us first note that the Bessel function does not pose any particular problem of singularities because it is an entire function of its argument. So the singularities may only arise from the remaining part of the integral, and in particular by the zeros of the denominator of the reflection coefficient, gamma, Tm. And as you know, the zeros of the denominator of a rational function are poles, so we have poles. But we also have square root functions because the vertical wave numbers, kz1 and kz2 in the two media, are defined by square roots, by the separation condition, and those square roots are multi-valued functions, in particular two-valued functions. So these square roots introduce branch points, and the integrand is multi-valued. Okay. In particular, those branch points are located at plus minus k1. These come from the square root that defines the vertical wave number in medium 1, as well as in plus or minus k2. And these come from the square root that defines the vertical wave number in medium 2. So we have two pairs of branch points, and to each branch point we have an associated branch cut. So we need to have 4 cuts in our complex plane, and since we have two determinations for two different square root functions, we have in general 4 possible values of our integrand. So in general, our integrand has an associated Riemann surface, which is constituted by 4 sheets. And those 4 sheets are schematically represented in this box. They are indicated with the Roman numbers 1, 2, 3, and 4. The first sheet, also known as a top sheet, is the sheet where the determination of the square root is such that the imaginary part of the wave number is negative for both wave numbers kz1 and kz2. Whereas, for example, if you go from 1 to 2, so you go now to the red sheet here, in this red sheet, the imaginary part of kz1 has become positive, okay? Or from sheet 1, you could go down to sheet number 3, the green one, in which instead the imaginary part of wave number kz2 has become positive. From sheet 2 and sheet 3, you can further go downstairs to the bottomest sheet, the one in blue here, number 4, where both wave numbers have a positive imaginary part. Now, the cuts, you need, of course, to go across the branch cuts in order to change Riemann sheet. And the shape of those branch cuts is largely arbitrary. They simply are required to join the branch points to infinity. The commonest and most convenient choice is the so-called Sommerfeld branch cuts, which are convenient because they are based on enforcing the condition that the imaginary part of the wave numbers is equal to 0, so that they separate the sheets where the imaginary part is positive from the sheets where the imaginary part is negative, as we saw in the previous slide. And as we have seen in the very first lesson of this course, those branch cuts have an hyperbolic shape. So consider, for example, two media, both lossy. So medium 1 is lossy, medium 2 is lossy, and so K1 and K2 are both complex numbers, and they belong to the fourth quadrant of the complex plane, whereas the opposite minus K1 and minus K2 belong to the second quadrant. Since the Sommerfeld branch cuts are hyperbolas, they run through the wiggly lines that are indicated here with light red for K1 and minus K1, and with dark red for K2 and minus K2. Note that in our problem, actually medium 1 was a vacuum, so medium 1 is lossless, so K1 is in practice real. And so those hyperbolas, the light red hyperbolas, collapse onto the real and imaginary axis, so they become those straight lines indicated here. Whereas if the medium in the upper half space is lossy, the remaining branch cuts, those in dark red, remain hyperbolic. Okay, so this is the situation of our complex plane. In order to move from a Riemann sheet to another one, you need to cross the branch cuts, okay, as we illustrated in our first lesson. Okay, having discussed the multivalued nature of the integrand, now let us say something about the occurrence of poles. Actually, it turns out that there is a pole, a single pair of poles, better, which is found by equating to 0 the denominator of the reflection coefficient gamma Tm. Now, the denominator of the reflection coefficient is, as you may know, the dispersion equation for Tm waves supported by this configuration, that is the two half spaces, in the absence of any excitation. So if we enforce that the denominator is 0 and we solve with respect to the radial wave number k rho, what we obtain is the wave number of the waves, the modes supported by this interface. And those are the poles of our integrand, and there are two poles which can be found easily in a closed form by manipulating this dispersion equation. And those poles are equal to plus or minus K1, the square root of the ratio between epsilon r and epsilon r plus 1. There are no other poles. These pair of equal and opposite poles are known as Sommerfeld poles. Now, we can easily see where they are located in the complex plane. They are located in the fourth and second quadrants. That is because, as you can see, if epsilon r, which is generally complex, has an azimuthal as an argument, the opposite of its argument is here phi, epsilon r plus 1 will have characterized by an angle psi, which is strictly less than phi from geometrical considerations. So if you express the Sommerfeld pole in a polar form, what you find is the expression reported here, where you can see the absolute value in front of the exponential. And in the exponent, you see that the phase is negative, and so we are in the fourth quadrant. Then if you enforce the minus sign in front of the square root, you of course end up in the second quadrant. This is allergy. by the way, not COVID. However, squaring, since we have squared in order to find these Sommerfeld poles, we have squared the two sides of the dispersion equation, obliterates any distinction of the square root branches. So we don't know anymore which determination of those two square roots at the left and right hand sides we need to choose. So we need to perform an additional analysis in order to discover what is the right determination. And now this analysis is again made by explicitly writing the left and right hand sides in polar form, by letting, for example, k1 squared as the product of its absolute value times a phase term, where delta is assumed to be less than psi. That is, the loss angle of the medium 2 exceeds that of medium 1, which is, by the way, vacuum, so it's lossless. So we may write the left-hand side, as you can see here, in terms of an absolute value, minus sign, and a phase. And the right-hand side can be written instead, as you can see there, again in terms of an absolute value and another phase term. Now, the imaginary parts of the square root have been chosen negative, and you can easily check that with this choice, the left-hand side and the right-hand side of the dispersion equation before squaring, they match. So the dispersion equation is satisfied. This means that the right choice for the square root is the one in which the imaginary parts of the square roots is negative for both wave numbers. And this is equivalent to saying that the Sommerfeld poles lie on the top sheet, okay, which is the sheet number 1, where the imaginary part of the wave numbers is for both negative. Of course, since the dispersion equation is an equality between two square roots, if we simultaneously switch the determination in order to have the imaginary part positive for both the square roots, the equality is maintained. So we also have poles on the bottomest sheet, that is sheet number 4, the one where the imaginary parts are both positive, okay? So we have a pair of poles on the sheet number 1, we have a pair of zeros on sheet number 4s, whereas on the remaining sheets, number 2 and 3, the square roots do not satisfy the dispersion equation, that is the denominator of gamma, but they rather satisfy the equation that is obtained by equating to 0 the numerator of the reflection coefficient, which is equal to the denominator up to the sign here. You can see there is a minus sign in the numerator, whereas a plus sign is present in the denominator. This means that if you are on the Riemann sheets number 2 or 3, what you get is that you have a 0 of the numerator. That is, the reflection coefficient goes to 0. And since when the reflection coefficient goes to 0, we speak of the Brewster phenomenon. That is, the Brewster angle is the angle that makes the reflection coefficient equal to 0. Then we call those zeros the Brewster zeros of our integrand. Okay? The location is exactly the same as the poles. So they are expressed by the same expression that gives us the Sommerfeld poles. However, on sheets number 2 and 3, this expression gives us zeros instead of poles, the Brewster zeros. Okay, so having said that, we are now able to explicitly represent all the situation in our complex plane of K rho. You can see there are 4 branch cuts with hyperbolic shape, the Sommerfeld branch cuts. There are a pair of poles, Sommerfeld poles, in the top sheet. What I have represented here is only the top sheet, where the integration path runs, because the integration path goes from 0 to infinity along the real axis of the top sheet, which is also called proper sheet. Note that here I have, for clarity, drawn the position of the Sommerfeld pole well distinguished by the branch cut, the branch cut and the branch point K1. But in practice, the Sommerfeld pole may be arbitrarily close to the branch points, plus or minus 1. That is because if you have a medium in the upper half space with a very large relative permittivity, then this ratio here inside the square root tends to 1, and so the value of Kp, of the wave number of the Sommerfeld pole, becomes very close to K1. And this causes a spike in the integrand, as you can imagine, because K1 is in practice very close to the real axis, or for a vacuum, it's exactly on the real axis. So this may be a problem from a numerical point of view. In addition, because of the presence of the Bessel function, the integrand is also oscillating, and the oscillation is particularly fast if the radial distance is large. That is because the argument of the Bessel function is the product K1 rho, and if rho is large, if K1 rho is much larger than 1, with z much less than rho, you have a very fast oscillating integrand. Here you can see, to give you an idea of the effect of the Sommerfeld pole on the integrand, a graphical representation of the absolute value of the integrand as a function of the complex variable k rho. Here you have the real part normalized with respect to K1, and there you have the imaginary part, again normalized with respect to K1. You can see here the cut, the Sommerfeld cut, and here you can see the level lines of the absolute value, which concentrate around the Sommerfeld pole, which is very, very close to the wave number, which is located on the real axis with the abscissa 1, and of course the imaginary part is equal to 0 because we are in a vacuum. Here you can see the shape of the integrand as a red line with a very peaked behavior, so a spike. Here note that the vertical axis is in a logarithmic scale. So there is a huge spike due to the closeness of the Sommerfeld pole to the real axis, where we need to calculate our Sommerfeld integrand. This beautiful picture is taken from a beautiful paper, which is the one reported here by the two probably most important experts in the field, Krzysztof Michalski and Juan Mosig. It's a paper in the Journal of Electromagnetic Waves and Applications about the Sommerfeld half-space problem. Since we need to avoid integrating the spike I have just shown you, one possibility in practice when you need to evaluate numerically a Sommerfeld integrand is to employ the possibility of changing the integration path that is offered by Cauchy theorem. And so instead of integrating directly on the real axis, as originally, you can detour around the wave number K1, in whose proximity we also have the Sommerfeld pole. For example, you can choose a path like this. You add a small imaginary part to K1, so you go with a straight line from the origin to K1 plus J delta, and then you rejoin the real axis sufficiently far from the wave number so that you have avoided the spike. And once you are on the real axis, you only need to deal with the oscillatory behavior of the integrand, which is also quite slowly decaying. However, there is a large literature on the treatment, on the numerical evaluation of those integrals, and so there are effective numerical quadratures. Note that the choice of the imaginary shift delta must take into account the value of rho, because if rho is very large, then the Bessel function, whose argument is K1 times rho, becomes wildly oscillating when you go into the complex plane. That is, if you go far from the real axis, the oscillations of the Bessel function becomes quite wild. That is because the Bessel function behaves like a cosine function. And so if you go into the complex plane, you get a behavior close to a hyperbolic cosine function. So the amplitude of the oscillations start to increase. So you must maintain your value delta limited to avoid that increase. And in particular, a good idea is to have delta proportional to the inverse distance rho, okay, in order to limit this exponential growth of the Bessel function J0 of the real axis. Okay, so this is more or less the numerical strategy that one needs to implement in order to have a satisfactory numerical evaluation of Sommerfeld integrals in general. However, in this course, we are not much interested in the numerical aspects, which are very important in practice, note, because we are more interested in physical insight, so on the analytical side of the Sommerfeld integrals. And what we will do, we will manipulate the Sommerfeld integral in order to change the integration path and thus be able to define different wave phenomena associated with the singularities in the complex plane. So we will look for alternative representations, which are not only more interesting from a physical point of view, but are also more convenient for numerical evaluation. To do this, the first step is to extend the original path which runs along the positive real axis, that's the Sommerfeld integration path, into the entire real axis, and that can be done by using standard relations that express the Bessel function J0 in terms of Hankel functions H01 and H02, so Hankel functions of the first and second kind and order 0. Now, the Hankel function of the first kind on the positive real axis can be related to the Hankel function of order 2 on the negative real axis and vice versa. So in the end, it is possible to integrate along the entire real axis by involving only the Hankel function of the second kind. So here you see the potential that solves the Sommerfeld problem expressed in terms of integrals along the whole real axis. That is the so-called extended Sommerfeld integration path that runs here along the negative real axis and also along the positive real axis. Note that I have drawn this extended Sommerfeld integration path in this way in order to emphasize that on the negative real axis, the path should run along the lower part of the negative real axis. That is because the introduction of the Hankel function has produced the occurrence of an additional branch point at the origin and the associated branch cut, which runs typically along the negative real axis. This branch cut has no physical meaning. However, we must avoid crossing it. So the integration path will run on the lower side of the wiggly line here. And also the path on the positive real axis must be drawn on the positive side of the real axis. That is because K1 that I have drawn here in the complex quadrant, fourth quadrant, is actually on the real axis for a lossless medium. And so we also need to choose if the path must run above or below K1, and it must run above K1, okay, by continuity with the case in which K1 is a complex number. Okay, so what we have is an alternative representation for the potential. Note that in this extension of the integration path, we have lost something. What we have lost is the possibility of calculating the potential on the z-axis, that is when rho is equal to 0. And this is why when rho is equal to 0, since rho is in the argument of the Hankel function, you would need to calculate the Hankel function with the argument equal to 0, which is impossible because the Hankel function is divergent logarithmically when its argument tends to 0. So this alternative representation holds everywhere with the exception of when rho is equal to 0. Okay, but usually this is not a problem, because what we are interested is typically in values of rho which are large, typically large in terms of the wavelength. The advantage of the extension of the integration path is that now we can use Cauchy theorem in order to further deform the integration path, and we can do that in the lower complex half plane because of the asymptotic behavior of the Hankel function of second kind, which allows us to close the contour, as you can see here in this figure, with a semicircular arc at infinity, whose contribution vanishes because of the exponentially decaying behavior of the Hankel function at infinity in the lower half plane. However, note that we cannot cross the branch cuts if we wish to have the integrand analytic and therefore be able to apply Cauchy theorem. So we need to detour around the branch cuts, as you can see in this plot, where the green curve indicates our integration path. Since the semicircular path at infinity is negligible, in the end, what we have done is that we have changed our extended Sommerfeld integration path to a pair of integrals that run along the two branch cuts here, plus the contribution of the pole, the Sommerfeld pole, which comes from the residue theorem. So in the end, our potential is given by an integral along the branch cut associated with K1. This is the Q1 operator here. The integral around the other branch cut that goes from the branch point K2 and is given by this Q2 operator. And finally, in blue, you can see the residue contribution that comes from the pole. Okay? Since each of those terms, the orange ones that come from the branch cuts and the blue one that comes from the pole, each of those terms is expressed in terms of elementary waves that are propagating also in the radial direction, because now you have the Hankel function instead of the Bessel function. And the Hankel function, as we have seen in the previous slide, asymptotically behaves like a cylindrical function. So it has a propagating rather than standing wave character. So for this reason, this alternative representation is called a radial transmission representation of the potential, okay? Whereas the former representation was the axial transmission representation of the potential. As concerns the residue contribution, this is the famous Zenneck wave. The name comes from Jonathan Zenneck, who studied this wave very early in the 20th century, in 1909. And this kind of wave produced much debate in the subsequent decades, because some people questioned about its existence and its role in electromagnetic phenomena, whereas the branch cut integrals provide a continuous spectrum of modes. In fact, this radial transmission representation is also called a spectral representation, because this gives us a representation of the potential in terms of modes. Whereas the branch cut integrals provide a continuous spectrum of modes, the single contribution of the Sommerfeld pole gives us the discrete spectrum, which is in this particular example constituted by a single wave, the Zenneck wave. The shape of the Zenneck wave is the one represented in this figure, where you can see the wave propagates as a cylindrical wave along the interface between the two media, and it decays exponentially on the two sides of the interface. So both in the upper dielectric half space and in the lower vacuum half space. The dependence on the radial distance rho is given by the Hankel function of second kind, which gives us a cylindrical wave that propagates outwards to infinity. And then you have the exponentials that give you the decay in both the vertical upper positive direction of the vertical axis and in the negative direction of the vertical axis. The amplitude of excitation of this Zenneck wave is, of course, proportional to the residue of the integrand at the Sommerfeld pole. It is interesting also to note the relation between the Zernike waves and the Brewster angle, as we noted that the wave number of the Sommerfeld pole is also a zero of the reflection coefficient located in a different Riemann sheet. Then we can introduce explicitly the Brewster angle by representing the Kp wave number of the pole as K1 times the sine of theta b. And if you do that and you calculate this angle theta b as the inverse sine of the normalized wave number of the Sommerfeld pole, then you easily discover that this is equal to the inverse tangent of the square root of epsilon r. And as you know from elementary electromagnetics, this is in fact the Brewster angle, which will be in general complex if epsilon r is complex. Note that at this angle we only have the incident and transmitted waves, because there is no reflected wave, as the reflection coefficient is equal to 0. And since both those waves must decay in magnitude, as you can see here in this plot, away from the interface, then, because they need to constitute a surface wave, note, however, that the incident wave propagates toward the interface. So this wave must increase in the direction of propagation. So it must be that its imaginary part is larger than 0, whereas for the transmitted wave, the opposite, the imaginary part of the wave number kz2 must be less than 0. So this explains why we cannot be on the top Riemann sheet, the one that with number 1, but we are on the second Riemann sheet. And by exchanging the role of the two half spaces, you can easily see that with the same reasoning, there must be also a Brewster 0 also on sheet number 3, okay, by reversing the role of the two wave numbers. The branch cut integrals can be written in particular by changing the variable of integration from k rho to kz. And of course, you will use kz1 for the branch cut originating from k1 and kz2 for the branch cut originating from kz2. And they can be written in this way, where you can see here I have introduced these double square brackets, which means the folded integrand. That is the difference between the integrand calculated on the top sheet with a plus and the integrand calculating at the bottom sheet with a minus sign. That is, you once use the determination with the negative imaginary part of both wave numbers in the top sheet, and another time you will use the determination in which one of the wave numbers has now a positive imaginary part. Okay, those two determinations are not equal, so the difference is non-zero, and that difference constitutes part of the integrand of the integrals that we need to evaluate. Note that also in this case, the Sommerfeld pole is close to the branch point, K1, so you still have a spike in the integrand and also rapid oscillations that are a problem from a numerical point of view. What we will do now, or better after a break, is that we will further change the representation and we will find another representation, the so-called non-spectral representation, which will provide us further numerical advantages and also the possibility of introducing some interesting physical considerations. But I think it's time to make a break, so let us see you in 10 minutes. Thanks. Okay, here we are again. Can you hear me? Are you still there?
Sì.
Okay,
Yes, yes.
thanks. Okay, so what we will do now is to perform a further deformation of the integration path in order to get to the so-called non-spectral representation. Consider, for example, the reflected potential. So let us introduce the image source at minus z1 and also the distance of the observation point P from the image source R. In terms of this distance, you can see from this picture that the radial distance rho is equal to R, capital R times sine z theta, whereas minus z plus z prime is equal to R times cosine theta, where theta goes from 0, belongs to the interval from 0 to pi over 2. We wish to evaluate the reflected potential, that is this spectral integral here, asymptotically for large observation distances. That is, the large parameter is k1r, which must be much larger than 1. In order to do that, we will prepare the integral in order to use the steepest descent approach. In particular, the first step is to extract the first order asymptotic expansion of the Hankel function for large arguments. That is, the blue part here has been factored out explicitly, and therefore we need to redefine a modified Hankel function which incorporates the reciprocal of that asymptotic behavior. Now, this modified Hankel function goes by definition to 1 as its argument goes to infinity. So it's a regular function at infinity. The advantage of doing this is that now we have explicitly inside the integral an exponential, the blue exponential here, that we may join with the black exponential, and therefore we are able to express the entire function, the entire integral in a canonical form. The canonical form is that the integrand is the product of a function f and an exponential in which the large parameter k1r is in the exponent. And this large parameter multiplies a function phi of k rho. In particular, this function phi of k rho is given by a constant minus j over k1 times kz1 cosine theta plus k rho sine theta, whereas everything else has been put inside the definition of the function f. So here you can see this bunch of things all collected together, including the modified Hankel function. Once we are in this canonical form, we may employ the saddle point or steepest descent method. And in particular, let us determine the saddle points by evaluating the first derivative of the function phi. If you equate to 0 this derivative, you will discover that you have saddle points of at the locations plus or minus k1 sine theta. And since the second derivative is different from 0 at those saddle points, those are first order saddle points. In particular, the second derivative has an argument which is equal to pi over 2. Okay, and this is important as we will see in a moment. Now, the saddle point determines the geometrical optics approximation to the reflected potential, since, as you can see, it selects the plane wave spectral contribution that gives rise to the reflected ray. So, among the infinity of plane waves that constitute the reflected potential, the saddle point singles out the single plane wave that propagates exactly at the angle theta, such that you get the reflected ray in geometrical optics. Okay? The steepest descent directions can be calculated in terms of alpha, the argument of the second derivative, which was equal to pi over 2, and so the steepest descent directions go as in the upper figure, okay, as indicated by the two arrows. And so you can see this is the shape of the steepest descent path. It is represented with a gray line that originates from the saddle point at k1 sine theta here in purple. And those two steepest descent paths go from the saddle point all the way to infinity, one on the left and the other on the right. Note that the path that goes from the saddle point on the left needs to cross the branch cut, the wiggly line in red, and so it goes on the second Riemann sheet. This is the dashed part of the line. Then it crosses again the wiggly line, so it comes back to the top Riemann sheet, and so we have again a solid line in gray here. Okay, here the arrows indicate the directions of descent along the path. Okay, so the saddle is the point where the absolute value of the exponential is maximum with respect to all other points of this gray line. Now, the function f is regular in the vicinity of the saddle point, so everything goes smoothly. We just need to evaluate it exactly at the saddle point without problems. Now, if we match the function in the exponent with a canonical polynomial phi of ksp minus s squared, and we evaluate the derivative of the original integration variable k rho with respect to the new integration variable s at the saddle point in the s-plane, that is at the origin of the s-plane, as we saw in the previous lesson, the ratio is given by this thing here, minus the square root of -2 divided by the second derivative at the saddle point. And if you do the calculations, this is the result, k1 cosine theta times the square root of 2j. So in the end, you can reduce your integral to this constant outside the integral times this canonical integral here, which is evaluated in a closed form, and after performing all the algebra, you will discover that the integral asymptotically behaves as a spherical plane wave that originates from the image source and is weighted by the reflection coefficient, the current reflection coefficient minus gamma. So everything is very clearly physically. What we have is that asymptotically, what matters is the incident ray, which gives rise to the reflected ray. However, in practice, you have a bundle of rays around the reflected ray, and these are associated with spherical wavefronts. So the iconal has spherical equisurfaces, and those constitute asymptotically our reflected field. Okay, so in the limit where when K1R is very large, asymptotically we have this closed form representation of the reflected field, and this is the contribution of the saddle point. Now, we'll consider what happens if you change the angle theta. Then the integral along the steepest descent path may or may not be the only contribution to the reflected potential. Why is this? Well, this is again the situation we have just illustrated. Now you have a single direction along the steepest descent path, since this is a path that is equivalent to the extended Sommerfeld integration path by using Cauchy theorem, okay? But if you now increase theta, it may happen that the saddle point now has become closer to K1, and here in gray, you can see that the steepest descent path now crosses both branch cuts. Now, if it crosses also the second branch cut, then in order to apply Cauchy theorem, we need to detour around the K2 branch point in order to come back to the top Riemann sheet. So we have to add this green folded integration path that allows us to come back to the top integration path. So in the end, you have the situation is more complex, because in addition to the integral along the steepest descent path number 1, the gray one, we also need to integrate along this vertical steepest descent path that goes through the wave number K2. This is by definition the so-called lateral wave that we will discuss more in depth in the next lesson. Consider that now, because of all those crossings of branch cuts, now the steepest descent paths lie in various sheets, For example, here the dashed part of the gray curve is in the second sheet, whereas the dashed dotted part of the gray and also of the green steepest descent paths, they lie on the third Riemann sheet. Finally, when theta tends to pi over 2, that is, when the observation point is on the interface between the two media at large distances, that is rho much larger than the abscissa of the source, then this is the situation. You have a pair of vertical steepest descent paths, the gray one and the green one. Both are folded onto themselves, and now we see that all four sheets are involved depending on the location where you are on the steepest descent path. Okay. Note now that the steepest descent path number 1 may be located to the left of the Sommerfeld pole. And if this happens, as in this figure, then the Sommerfeld pole is captured in the deformation of the integration contour from the orange extended Sommerfeld integration path to the pair of steepest descent paths. And its residue contribution comes from this circle in blue here, must be added to the representation of the potential. So in the end, we get a representation in which you have a pair of steepest descent path integrals plus a residue contribution. Now, this pole contribution, here we have a slide in which we make a small taxonomy of the contribution that originates from the pole. If the dielectric represents a lossy ground at radio frequencies, which is important in radio propagation applications, then, as we already said, the Sommerfeld pole is associated to the Zenek wave. And in this case, it is never captured in the non-spectral representation. So it is located, as in this picture, on the left of the gray steepest descent path number 1. So there is no residue contribution. However, in other cases, it may be captured. For example, if you consider a metal like silver or gold at terahertz or optical frequencies, then the Sommerfeld pole is located on the right, as in this picture here, of the steepest descent path number 1, and it is therefore captured, and it gives us a residue contribution. In this case, it is not called a Zenek wave, but it is called a surface plasmon polariton wave, SPP. This is something you may have encountered in your studies. Surface plasmon polaritons are a particular kind of surface waves that propagate along interfaces, typically along the interface between a metal and air, and whose field decays exponentially on both sides of the interface, exactly as the Zenek wave does. Basically, because the SPP and the Zenek wave are the same wave, they are the wave that originates from the Sommerfeld pole. Okay, the Sommerfeld case is when the pole is not captured. The plasmonic case is the case when it is captured. And here you can see those cases are indicated with different colors in this table. The two columns of this table represent two limit cases. On the left, the case of a dielectric with high loss, in which case you have the Zenek wave in the Sommerfeld case and the surface plasmon polariton in the plasmonic case. Whereas if you have a low loss medium, the terminology is a bit different. For a low loss medium, if the pole is not captured, you have a Brewster mode, whereas if it is captured, it is called a Fano mode. Okay, this is just to introduce some terminology which you may find in the literature. Okay, now we will say something about the role of Zenek or surface plasmon polariton waves. As we have seen, our potential is represented in terms of two integral contributions along the steepest descent paths, and this is given by the orange terms here, plus possibly a pole contribution which may be there or it may not be there, depending if the pole is captured or not. In the Sommerfeld case, the pole is not captured, and so you don't see this blue term here, okay? Now, in both the Sommerfeld and plasmonic cases, so both when the pole is captured and when it is not captured. However, it is very close to the branch point, K1. So it produces a spike in the integrand, and it may give a significant contribution to the value of the branch cut integral, also in this non-spectral representation of the surface potential. So we need to explicitly deal with this difficulty. Now, look at what happens in the complex plane of the variable s, which we introduce when we evaluate asymptotically the integral with the steepest descent method. Now, the saddle point is located at the origin of the s-plane. The steepest descent path is the real axis of the s-plane. The original path is the black one here. And when you are in the plasmonic case, you have a pole that is captured. When you are in the Sommerfeld case, you have a pole which is lower than the real axis, and therefore it is not captured. The function f, capital F, in the integrand is defined, as you can see here, in terms of the folded integrand, tilde f. Now, if the dielectric has some losses, which are not negligible, then the exponential that involves the K2 wave number will be negligible in absolute value with respect to the exponential that involves the K1 wave number, whose absolute value is equal to 1. So the integral that originates from the K2 wave number that we have termed the lateral wave typically is negligible with the integral I1. So we can disregard the integral I2 and concentrate on the integral I1, for which the situation is the one that I have just described. Okay. What we need to do in order to deal with the difficulty of having a pole very close to the branch point K1 is a trick which consists in first subtracting the pole from the integrand and then re-adding it back. The integral thus splits into two contributions. In the first contribution, IP, we have removed the pole because we have added to the integrand a function whose contribution is that of removing the pole at the Sommerfeld pole SP. Okay, of course, we need to subtract back what we have added, and so we get a second contribution, IQ, which contains only the Sommerfeld pole here, and SP here is defined as the square root of J times Kp minus K1, and BP is a numerical constant, okay, which involves also the Sommerfeld pole. By proceeding in this way, the modified integral IP here, the one without the pole, can be integrated with simple quadratures, because now the integrand is well behaved. There is no sharp peak because there is no pole anymore. And the integrand, by the way, is also not oscillatory and very fast decaying because of the presence of this exponential here, which is the typical Laplace exponential that we find along any steepest descent path. Okay, so in this case, the larger is the distance rho, the better is the behavior of the integrand because it decays more rapidly. Okay, so what is complicated with the original integration path is simpler with the steepest descent path. Now, there remains to evaluate the integral IQ, but fortunately this compensating integral IQ admits a closed form representation. And in fact, by manipulating this integral a little bit, it can be represented as the function of this Gaussian integral, whose value is known in a closed form. It's 1/2 of the square root of pi over rho here, plus a second integral I sub s, which can be evaluated in terms of the so-called Faddeeva function, W of z, which is a scaled version of the complementary error function with imaginary argument. Such function W admits, in fact, an integral representation which is very close to our IS integral, when the imaginary part of its argument is positive. Note that since the imaginary part of our pole may be instead be negative, since we may be in the Sommerfeld case, then in this case it is necessary to extend the validity of this representation of the Faddeeva function to take into account the contribution of this pole by adding to the integral the residue contribution of this pole. So taking everything into account, the final result is that the compensating integral, IQ, can be given a closed form in terms of the so-called attenuation function. This is a historical name that was given by the people who studied the Sommerfeld problem almost 100 years ago, or more than 100 years ago, Zennek, Sommerfeld, Norton, and so on. This attenuation function is defined in terms of the Faddeeva function W, and its argument P is the so-called numerical distance, which, as you can see, is an adimensional quantity, which is the product of the radial distance ρ and the distance in the complex plane between the Sommerfeld pole and the wave number k1, that is the branch point k1. Okay, so collecting all these results, the final expression for the steepest descent path integral around k1 is this one, where you can see there is the contribution of the integral IP, which can be evaluated numerically, and there is the closed form contribution of the compensating integral. The latter contribution is discontinuous when the sign of the imaginary part of SP changes, because this means that the Sommerfeld pole crosses the steepest descent path. So the Sommerfeld case now turns into the plasmonic case, and now the pole is captured. However, this is not a problem, because this discontinuity in the representation of the SDP1 integral is exactly compensated by the introduction of the residue contribution of the pole that is now captured. So in the end, the overall potential remains continuous, as it must. Finally, the same pole extraction can be used if you wish to evaluate asymptotically the steepest descent path integral. And you can do that in a very simple way, since we are on a steepest descent path. So you simply enforce the theory of asymptotic expansion using the steepest descent method. The result is this one for the regular integral. And since we are able also to evaluate asymptotically the attenuation function fp, f of p, in the end, this is the asymptotic result for the steepest descent path integral in terms of the so-called modified attenuation function. And in the end, this is a useful result in practice because it's accurate toward the ρ to -2. So with this analytical result in your hands, you may evaluate asymptotically with a good accuracy the Sommerfeld integrals for large distances from the source. Okay, I guess this is everything for today. We have discussed the Sommerfeld problem, which is an old problem. It's more than 1 century ago. It produces an enormous literature. In this literature, there have been much debates, and in these 3 papers by Michalski and Mosig, the history of the problem is recalled, and the theory is masterly exposed. So these slides are more or less taken from here and there in these 3 papers that are highly advisable. They are written beautifully and very clear. So if you're interested in these problems, I suggest that you download and read them. Next time we will go on in this vein, again considering non-spectral representations, and we will discuss other wave species. In particular, we will discuss at length the lateral wave, and we will say something about leaky waves. Thank you very much for your attention. As usual, if you have questions, you may ask them here or whenever you wish. Thank you.
Thank you. Bye-bye.